Question 1 says, what's the following example of something that's not a square matrix? In this case, we've got an inverse matrix has to be a square matrix. A transition matrix is generally, yes, a square matrix. Permutation matrix would involve some sort of shifting of the numbers, but if you had, for example, a 1, 2, 3, a permutation matrix would need to be a 3 by 3. So yes, that would be a square matrix. And the last one is communication matrix. That would also be a square matrix. So A has to be the answer for that one. Look at question 2. Question 2 says students can select woodwork, fashion, coding. Matrix A shows the number of students who choose each elective. When A is added to matrix B, what does the information show? In this case, we've got D, the total number of students in both classes A and B who choose each elective in this case. Question 3 asks us, which of the following matrix doesn't produce a matrix with 5 rows and 3 columns? In this case, if we look at the rows and columns of this one, this is a 3 by 5 and this is a 5 by 3. You can see we want 5 rows and 3 columns at the end. This one only gives us a 3 by 3. Let's just take another one for example. This is a 5 by 1 and this is a 1 by 3. So yes, it will end up with a 3 and a 5 and 3 in that paint. So that means we've got C as the correct answer for this one. Alright, question 4 talks about a particular scalar multiple in this case. So we need to work out what that is. We go 13.8 divided by 11.50 and we get the answer 1.2. So if we go 15 times 1.2 we get an answer of 18 and E is the answer in that case. Alright, question 5 talks about possible flight routes from V, W, X, Y and Z. It says how many ways can people travel from town Y to town B without using the same route more than once. So we want to get from Y to V. And if we investigate the situation, we've got to go from Y to V. Well, we've got YV as our first route. So we've got at least one. But we could also travel from Y to Z. So we'll look at Z first, and I'll show you the other alternative for X. So if we go to Y to Z, okay, the other route from Z to get to V is YZV. Now, obviously, you don't want to go YZ, Y in this case, because you're going to be traveling more than once. So there we go. The answer is at least 2 in this case. What we're going to do now is going to have a look at what happens if we go through this way. What if we go to Y X? Okay, and if we go through YX, we have to end up in W. So YXW is that pathway. Now, when we end up in W, we can go to V. Okay, so the one solution to this is to go straight to V from this one. Another solution to this one could be going to, we can't go to X, because if we go to X, we'll end back in W again. So if we go to W to Y, that won't work out, because we're revisiting Y. And if we go to W to Z, okay, what happens if we go to Z? We can go to V from that point, or in this case, that's really it. So you've got 4 potential paths to go from Y to V without revisiting. Alright, next one, question 6. It said matrix P, Q, and R are square matrices. Inverse of matrix of Q. So inverse of Q is equal to P. Matrix R is the transpose of matrix P. And you can see in this case, we can also make the assumption that the inverse of P is also Q, because there's that reversibility that exists there. So it says all 3 matrices are defined if. Now let's look at the fact that all these 3 matrices, so we've got R, P, and Q, they're all related to each other. So if one is not defined, the other one will also not be defined. Let's have a look at the determinants, because the determinant, remember, if the determinant of a matrix is 0, it doesn't have an inverse, and it's not defined in this case. So its inverse is not defined. So you can see with Q, you've got 2 times 4 minus 8 times 1. That's not defined. Determinant for this one is 0. And determinant for this one is also 0. So we've got to be very careful now with this one, with A and B. Now with A and B, we're not talking, we don't, if you just look at the first instance of this question, you would say B is the correct answer, because obviously this one here has an inverse, a determinant of 0. But we just need to make sure we check this, because R is the transpose of P. So, so we should have checked that for this one. So the R is the transpose of P. In this case, sorry, just a bit of a mess up there. So I think you need to find the transpose of that. In this case, we just need to make sure the determinant of this is not 0. So in this case, B is in fact the correct answer, this one, because the determinant for that one is 0. Alright, so this particular question wants to have a matrix that ends up with 2 conditions. The total number of cakes sold in the week and the total number of sales from selling all the cakes. So, when we have this particular matrix, we've got sale prices and number of cakes sold, and it seems like we want to be able to add up all the matrices, A plus B plus C plus D, and then, sorry, we don't want to add those up, we want to add E plus F plus H, okay, and then from this point, the sale price, you want to go the number of cakes that you sold times the sale price, so AE plus BF plus CG plus DH. Okay, now from this point, if you look at each of these responses, A won't get you that. A will only get you that total number of sales. If we look at this matrix here, okay, again, this really will solve nothing. It's just A times E, B times F. It really doesn't get you anywhere with this one. We want this condition here, the total number of cakes sold each week, to be the summing. So it's got to be either between B and D in this case. Now, if we look at A, B, C, D, we'll go A times 1, B times 1, C times 1, D times 1. That just adds up the sale prices. That doesn't actually add up the total number of cakes sold. So if we look at this, E, F, G, H, okay, D will get you that final matrix that you require. Okay, next one. Alright, now it says how many of these statements are true, and when we're talking about this particular transition, we've got a transition matrix here, and we've got S1 over here. Now, you'll have to use your CAS with this one. I've gone through the working of this, but we'll look at how many of these statements are true. So it says the first one, the highest number will always be K. So if we go through one transition of S1, we actually find that the highest value in this case, for J, K, L, and M, this is not the highest value. So in fact, that statement there is false. Now it says here all 4 numbers in the matrix S0 are equal. Now we're given S1. So in order to get S0, we can find the t to the power of minus 1 of S1. And that'll give us S0. And when we actually do this, we find that all the numbers are equal. Yes. Now, the next one says 30% of workers at L one week will remain at L the following week. So the loop, in this case, that is true. Next statement says of the workers who started at J, 20 will still be at J 2 weeks later. Now, we don't really know that at this point. We could go through a couple of transitions. So I'm guessing for this one we could go through to S2. In this case, this one's actually not true. And the last one is, in the long term, the number of k is going to be to the power of, equal to 152. When we go through transition to the power of, say, 50 times S1, we do get 152 there. So in this case, that's correct. So C is the most correct answer for this one.